attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
Okay, so hello everyone and welcome to Object Lifetime. So I want to start by painting a picture for you of what inspired me to come here today, talk about Object Lifetime. Of course, we are only 1 minute in, so I did blur a few things not to give it away. But this piece of code, it's a representation of a problem that I hit a few months ago. It was a deadlock, the type of problem that really makes you think, okay, there's something wrong here. I know how C++ works. So the only explanation for what is happening here is, of course, a bug in the compiler. Not at all, it's something that I'd be thinking incorrectly from the language. So I don't know if you are familiar with this meme, but that was pretty much me after realizing that I didn't really fully understand the rules for object lifetime in C++, even though I was working with C++ for more than 10 years now. So what is object lifetime anyway? So I went to the standard, I started reading about object lifetime, and it went on and on and on, and it spent like 6 pages only for the object lifetime part. Not to mention everything around that you need to check and to go see to fully understand something that they were saying. So I want to start by really setting some expectations here. What you can expect from this talk. You can expect a review of object lifetime, of course, it's the name of the talk. You can expect a little bit about RAII, or RAII, whatever you want to call. But really what we are going to focus here is beyond this basic lifetime. And we are really focusing on the common pitfalls that you might face when you are working with objects in C++, which I believe is pretty much always, right? What you should not expect from this talk is any mention or explanation about value category. What I'm saying here is I'm not going to mention L values, R values, or anything like that. This is a very complex topic, and my idea for this talk is to have a talk that is very digestible for someone who might be starting with C++, at the same time that it's easy and might have something to add to someone who might know C++ for a while as well. For this talk, of course, I'll be ignoring a few things of the language, namely unions, arrays, and a detail here and there that will help with the progression of the talk. After all, I only got 1 hour of your time here today. And although we usually really see a lot of assembly code, there will not be any here today. And again, the idea here is to have a very digestible presentation for anyone, no matter the level of knowledge of C++. So, hi, my name is Thamara, and I'm a software engineer working at Cadence. I work doing software that does the formal verification of hardware, which you might not know nothing about, and if you want to know, come chat with me. If you want to know more about what is formal verification or know more about Cadence in general. I have been doing C++ for 10 years now, and I think really the key word here is that I've been learning C++ for 10 years now. And if something, this talk is really showing that we can still learn a few things here and there, even though we've been working with the language for such a long time. And also something about me is that I cannot decide if I want to call the namespace for the standard library stud or std. So namely, I just ignore that altogether. But let's talk about object lifetime. Actually, before that, let's just do a very crash course on two important concepts here, which is storage and non-vacuous initialization. And again, it's a crash course. It's not meant to have a lot of details. It's just really a high-level view, just to get everyone close to the same page. And I do encourage everyone to ask questions as we go. If you don't want to ask questions now, feel free to take a note at the slide number. It will be quite a long list of slides, but that's mainly because I do animations the old way. But just take a note at the name or the number of the slide, and we can come back later. But on the storage duration, in C++, we have mainly 4 storage durations. It's basically the way of us to categorize what is the way that the memory, or how is the memory going to be kind of allocated for an object. I'm saying not the formal words here. Sorry about that. But basically, we have 4 types. We have the static, which is preceded by the word static, that will dictate that an object will be allocated when the program begins and deallocated when the program ends. We have the thread locals, which is similar to the static, but allocated when a thread begins, deallocated when a thread ends. We have the dynamic, which is something that we are more used to see. This is the type of objects that we initialize using the new and delete using the delete keyword. And we have automatic, that is kind of a catch-all thing here, that is not objects that are static, thread local, or dynamic, and their lifetime is dictated by the block that they are in. Again, really, just a high-level view here. If you happen to be here on Monday and catch this session from Jason Turner, he went into more details of storage and with some very interesting examples. Unfortunately, this is a session that is not really recorded, but I mean, if you had a chance, I'm happy that you do. Either, if not, maybe you can just send a message to Jason and convince him to turn that talk into maybe a video on C++ Weekly. For this talk, I will be mostly focusing towards the objects that are either dynamic or automatic. So this will be our focus for today. The other thing that I want to mention is non-vacuous initialization, which is a really fancy word for talking about an object that has a constructor other than the trivial one. So what is objects that have a non-vacuous initialization? These are objects that, for example, have a constructor. Even though it's empty, it's said to have a non-vacuous initialization. There are other rules, for example, of objects that, although they don't have a constructor, they have virtual functions, then it's also non-vacuous initialization. And for the reference, the objects that have vacuous initialization, they are the basic types such as int, floats, booleans. They are classes that either doesn't have anything or have only the basic types such as ints. So that's the basic stuff for us to really start talking about when the lifetime of an object starts. So what does the standard tell us about that? It tells that the lifetime of an object starts when the storage is obtained, and if the object has a non-vacuous initialization, basically if it has a constructor, then the constructor have finished. So the constructor is complete. On the other hand, if the lifetime of this object finishes, either because the destructor has been called or the storage was released. Of course, there are some other details in the case where you can reuse storage, but we are not going to dive into that right now. Let's go through some examples just to warm up and to get a hang of what we are going to talk more today. So, talking about constructors and destructors. Usually, I mean pretty much always when we are talking about constructors, object lifetime, we have examples like this, We add some print messages just to help us visualize what is the flow for the lifetime of this object, and this is what I'm doing here. And we start by defining an object A of type foo, which should, of course, call the constructor, and we will see a message such as foo, constructor foo. Then we have the start of a new scope, and in that new scope, we declare an object B with the type foo, and we see another constructor, another instance of that message from the constructor here as well. Now we reach the end of a scope that declared one of the variables, one of the objects that we are working on. And because this object has an automatic storage, then it's called, the destructor is called here, showing us the message that we added. And finally, the object A is destructed at the end of the main function here. That's easy. The same thing would happen in the case where we have dynamic allocation. So in here, we declare a pointer. So the pointer itself is an object, but it points to another object that we have not yet initialized. Then in another scope, we do initialize this object by using new, foo, which we will see the message that is being printed. Then we reach the enclosing block, or the closing block for this scope, but this is a dynamic variable. There is nothing that's going to happen here. Foo is still alive in memory. There is nothing really different here. And then we reach the point where we are going to delete that object. So we have the control over the lifetime of that object, and we decided to end that lifetime by calling delete, which we'll call the constructor for that, the destructor for that object. And then we finally reach the end of the function, which in this case will end the lifetime of the pointer, but nothing really happens here. If we were to take away the delete here, even though the pointer is getting out of scope, nothing will happen, we will have a memory leak. Maybe a more interesting scenario is this one. In this scenario, we, again, instantiate a full object, but this time we print the message, we will see that, and we throw an exception on the constructor. In this case, although we are seeing the message, because we did pass on the message before we have thrown the exception, even though we are seeing this message, it doesn't mean that the object was initialized. The constructor has not finished it. So we can continue with the execution of our code, and even when we reach the end of the function main here, we will not see any message related to the destructor of the object, because the object was never really initialized. So there isn't really an object here to start things with. And that's what is highlighted here. So again, the lifetime of the object starts when the storage is obtained and when the constructor has finalized. Otherwise, it will not start. And just to review, the lifetime of the object ends when we have the destructor being called, the call for the constructor has started, or the storage has been released. And if we put it all together, and what we'll have, another example is something like this, where we have an object that is foo1 being created. We will see that object being created. We start a new scope where we create another object foo2. We finish that scope, and then foo2 is released, so we see the message that shows on the destructor of the object foo. We see that again for another object, for foo3, the construction of this object, and again for foo4, the constructor is also called. And then at the end, we need to destruct these objects, and the way that we do that is by calling the destructor on the inverse order, the reverse order that we call the construction. So we do see the destructor of foo3 and then the destructor of foo1. In this case, we don't see any destructor of foo4 because we never really deleted that. So it's a memory leak in here. So that's pretty much the lifetime of a single object in a nutshell. So in here, now I'm gonna do a little bit of opening a scope on this talk to talk about RAII. Because what RAII is doing is tying the resource allocation and the allocation to the lifetime of the output project. So RAII is resource allocation is initialization. You might remember that Bjorn has mentioned that on his keynote on Monday as well. And it's a very common technique that we can use to avoid having to deal with, individually with some resources that might lead to problems. So a very common example of RAII in action is that we can encapsulate an array in a way that we can manage the allocation for the memory and make sure that on the destructor we deallocate that memory, we free that memory, and the user doesn't have to deal with that at all, so we avoid issues such as memory leaks. And the management of resources such as memory is just an example of something that you can do using RAII. So heap memory allocation, mutex, threads, file management, even loggers on your code, and everything else, this all can be improved by using RAII. And it's not really a coincidence that many of those, we actually have that, that feature or that component inside the standard library. So unique pointers, lock guards, and everything like that. From the string that you use, that you don't need to worry about how the buffer is allocated when you are appending new things, to things like auto-joining threads. Everything has been encapsulated in the standard library using techniques such as RAII. So although it's saying including on the STL, I would actually say that it's most of the STL that has been built on top of RAII. And of course, I mentioned that I'm gonna talk just a bit because RAII is a very, I wouldn't say complex, but we can really dive in and do really cool stuff with that. So I do recommend this talk from last year's CppCon that goes into more details of this technique, so feel free to check that out. So that was pretty much object lifetime. But the truth is that what I want to really talk here is not really the start or the finish. It's all the tricky parts that are in between. So let's talk about that. So to start, I don't know if you know Mad Libs. I don't think it was that famous in Brazil, where I'm from, but I heard that in the US it was more common. But for those who might be too young to know, it's this kind of game where you are asked to give words without any context of how that word will be used. So you might be asked to give a noun, a verb, or even a part of the body, and then you put this into this kind of text, and then you have like a funny story that you can read out loud. But of course, we are in a C++ conference, so what we'll be working on is on this piece of code. And because we only have 40 minutes now, let's limit the types of things that we can fill these blank parts with. So we will be mostly working with const reference, the object, const objects, we will see. And we will fill in the blanks here and reason about this code. So this actually came to me after reading Absel. I'm so sorry if I'm pronouncing that wrong, but this is a page, a blog, a portal, whatever the name, that has quite a lot of tips related to C++, so I do recommend that you check that out. And in one of those issues, there's the C++ Tips 101, it does start with that, and I thought it was a really fun way to introduce some of the topics that I want to mention here. So without further ado, let's start. Pretty basically, let's return an object by value, an object foo, on my getFoo function, and let's initialize vol with foo. Let's declare vol as foo as well. And just to make things clear, not really clear, but a little more interesting in this case, let's fill in the function here, returning a temporary object foo. So we can start thinking, how many objects are we talking here? How many objects does exist here? Maybe one, maybe two. If you want to think there may be more, I don't know. But I would say that mainly there are two types of answer for this. The first answer is that the person will consider foo, the foo that is constructed on the return function of getFoo, an object, and vol, another object. In this case, we actually have just one object. Actually, we only have vol here. And the reason for that is something that you might be already familiar, which is return value optimization, sometimes named return value optimization, but very high level, on a very high level view, what it's actually doing is just seeing that you are constructing a temporary object, and instead of constructing and then possibly calling a copy constructor or move constructor, it's initializing that object actually on the storage that was allocated for the variable vol, the object vol there. Actually, there are, if we want to generalize this a little bit, there may be some cases, of course, when the RVO, return value optimization, doesn't really work. So maybe the best answer here would be that usually it's one, but at most we will have like a move constructor here. This talk is not really focused on RVO. This is a much complex topic, and of course it's very dependent on the implementation, it's very dependent on the compiler, so we will not go into the details here. Let's jump into the second example. In the second example, we are returning a reference, but we are still initializing, we are still declaring vol as just the object, so foo vol. In this case, we will most likely have a copy constructor indeed happening here, because we can't really reuse that memory from an object that we don't own. And if we add some const in there, again, it will not really matter. We will most likely be hitting either, we will most likely be hitting the copy constructor. So constructors is a whole big deal. The way that you set up those in your environment or in your object, it's another topic, which we will not be covering today. But I want to mention that on Friday, on the same room, there is going to be a talk on the rule of 5, which help you kind of create a guideline on how do you set up your constructors, and hopefully they will also be covering more details, this difference. For now, let's continue with our examples, and let's jump into more complex details. And then I said complex, and I show you the case where we are just returning a const reference and initializing a const reference. So what's complex about that? So this, let's just consider that we are returning here the member that we have on the object obj. So we only have one object here, right? I mean, if we are talking about foo, we only have one foo object. But of course, we have the reference as an object itself. And most likely, there will not be a problem with this, but there can be. So what's the problem that we can have here? The problem is dangling references. So what's dangling reference? Maybe you have heard about dangling pointers. It's kind of the same. To go over these, let's illustrate with an example again. So in this example, I just have expanded the foo and the bar objects in a way that foo also has a bar object inside. And then we can start executing the main function by initializing the foo object. And we will see not only that foo is initialized, but we also initialize bar. And take a look at the order here. It's not the focus here, but it's interesting to see that first we have initialized the member, then the object itself. But then we create that const reference variable. So the reference itself is an object. And we have assigned that to a reference to the bar that lives inside object f. Then I can use this reference to access the integer that lives inside the bar. No problem at all, this is fine, works great. But then f got deleted, either because we have deleted or because of some of the flow that you have, this object gets deleted. Then objects are deleted, and then you try to access the member again. And oh no, we have that two words that we don't like at all, UB, undefined behavior. So dangling references are not great. It can lead to undefined behavior. So as much as we see a code like this, and you will see a lot of code like this, most times it will be fine. You will have some control of what the reference, where does the reference is referring to make sure that the lifetime of that object is under your control, but there might be times where it isn't. And those times will be really hard to work around. If we take away the const on the return, again, the same problem. And again, if we just take away the const when we are declaring the reference, with a plus here that we might now be messing up with the content of something that we should not, but this is more towards the design of your interface. It's not really a problem related to the object lifetime. The message here is that although it sounds very simple to create const references, be careful when we are doing that related to objects that you don't know or you don't have control of their lifetime. Okay, so next example, we are still returning a const reference, and we are initializing a non-const reference. I think my words here might already give it away of what's happening, what might happen here, and it's a compilation error. So the compiler will not allow us to take away the const and declare that line of code. And if we instead return the object by value, so we are returning a copy of an object, for example, but initializing a reference, the compiler will not like it as well. It will complain about a non-const value reference, and will not allow you to do that. But then we can put a const in that reference that we are initializing vol. So we can declare vol as a const full reference, and because we are returning full, we are returning a temporary object. Then, depending on how much have you worked with C++, you might think, okay, this will not work as well. The compiler will complain about that, but no. The compiler is fine with that. It actually allows that to happen because of one specific part of the language, of one specific rule of the language, which is the reference lifetime extension. So while we were going over these examples, I have been mentioned a lot temporary objects, returning temporary objects, but we never really talk about that. So let's go and talk about temporary objects. Of course, let's talk about their lifetimes. And what the standard says is that the temporary objects, they are destroyed as the last step in evaluating the full expression that contains the point where they are declared. So, again, the temporary are destructed as the last step when evaluating the expression from where they are declared. This might be too much for some people, so let's go into an example, and again, let's continue using our full and bar classes. And in this case, we have the full class return a bar, so create a bar and return that by value. And then we have some code, some functions that we work on this class of this structure of ours. So we do something that take different types of parameters, and we have do something else that just do something else. And then we call those functions. But before we dive into those functions, take a look that I'm actually chaining those. I'm using a comma to separate those. So when we are talking about full expression, in this case, we are talking about evaluating everything. So from the construction of the temporaries here to the call of do something and do something else, only when we reach the semicolon at the end, then we have reached the full expression. And this is very relevant for what we're talking. Another thing that I want to mention is that the order of evaluation of parameters and functions is really dependent on the implementation. So I believe that Clang does left to right and GCC does right to left. I might be wrong, but the idea is that the standard does not define, but of course the implementation must have some kind of rule to follow here. Just for the sake of example, we will be doing left to right. So let's evaluate this function step by step and see how is the lifetime of these objects that we are creating, how do they behave. So we start with full one. Of course, we construct that full one. Then we construct another object full two, and we access that integer. And we see the constructor being called here. Then we construct another object full three, and from that we call getBar, which, if you remember, just creates another temporary object and returns that. So we see full three and bar three being created here. Then, just for the sake of example, we can create also a string and access the buffer from that string, and we would see the construction of that string as well. We have now reached the end of the evaluation for do something. Actually, the end for the evaluation of the parameters. So now that something is evaluated, but the full expression has not come to an end yet. So we now evaluate, do something else, which will do something else, and then we finally hit the end of the full expression. And that's when we will release or we will destruct all the objects that were created during this evaluation on the reverse order of creation. So we will see the string being deleted, bar 3, full 2, and full 1. So everything needed to be evaluated completely for us to really release the resource and to delete the objects that were created halfway there. Another example here, we have a function that takes on a concept reference to an object and just return that, returning a concept reference as well. And we have do something that this time, let's assume that it's working on top of the concept reference that is receiving as a parameter here. So again, let's go step by step here to evaluate this full expression. So again, we start with the creation of foo. This object remains alive. It remains alive in this scenario, so we are passing that reference to the function ret_temp_ref, and then we evaluate, do something as well with that parameter that it receives. And finally, we reach the end of the full expression, in which case we delete the object foo here. So that is the basic rule for the lifetime of temporary objects. But of course, as we will come to see, for every rule there are exceptions. And for this rule, there are 3 contexts or 3 exceptions for that. So the first 2 contexts in which the lifetime of the temporary might be, the temporary might be destroyed in a different point other than the end of the full expression. So those 2 first examples, we can ignore them. We will not be talking about that. We will be focusing on the third case, or the third context, which is the scenario when we have a reference bound, when we have a temporary bound to a reference. This is what justifies the reference lifetime extension, because it states that the temporary that is bound to a reference has its lifetime extended, or the object persists until the lifetime of the reference itself. So another example, again, we are just continue printing out some information just to see what's happening each step of the way. We have this time a function I that returns an int by value, so returns a copy, let's say like that. And we also have a function RAII. I should have thought about a better name for that, but it basically returns a reference for the integers that lives on the object foo. So the first thing that we do on the main is to create or to define a const reference v1 and assign that to a temporary object foo1. So we will see the object being created, and if it were not for the rule that we saw that extends the lifetime of this object, by reaching the semicolon there, the object would be destructed. But no, we are binding that to a constant reference, so this is fine. The lifetime of object foo1 will persist as long as the lifetime of the reference v1, which in this case is the end of the main function. Then on the next line, we have a const into reference, v2, that is assigned to foo2.m1. So basically, we are creating a temporary object, and we are accessing directly a member of that object. So this will also allow for the lifetime extension. So there are a few rules here and there that will define when exactly the lifetime does kick in, the lifetime extension. And by accessing a direct member of the object, it allows, or it fits into the rule set that will extend the lifetime of this object. Then we have a third object, foo3, and we access, we call I from that, which will return an object, an integer here. So in this case, we do see foo3 being created and destroyed in this case. But what we have is actually the integer here having its lifetime extended. So in this case, it's a new object, it was a temporary object that we created, so it's fine for it to have its lifetime extended. Finally, we create another object, yet another object, but this time we call IR from that, which returns a reference. So because we are doing that, not directly accessing the member, then in this case, the lifetime extension will not work here. In this case, we will see foo4, and the destructor of foo4 being called. And as a matter of fact, we will have another dangling reference here. Finally, as we reach the end of the scope where all these references were declared, then we can have the objects being destroyed, and again, in the reverse order. So we will have the int being destroyed, then foo2, then foo1. And that's one of the exceptions, right, for the temporary object lifetime, but there is an exception to the exception. And that's when things really got out of hand for me when I was reading that. But basically, the idea for these exceptions, there are a few here that I'm going to go through. The first one is just a reiteration regarding the lifetime extension, or how the lifetime of temporary objects should behave when they are being bound to parameters, to constant reference on parameters. So this example that we saw before, where we were creating a temporary called foo1 and passing that to a function that takes on a reference, this whole code works not because of reference lifetime, but because of the main rule for lifetime of temporaries. The second rule is basically just to not maybe create problems for us when we have something like a function that returns a constant reference and you return an object, a temporary object that was created on the return function. In this case, that object doesn't have its lifetime extended. So just by having a function return a constant reference, that will not work as a lifetime extension. If you want that to work, you would have to have the function return foo by value, and then by calling constant foo reference equal to get foo, then it should be the lifetime extension. And then there are a few other details that I'm not going to go into right now. But I want to share one other case that really kind of, I wasn't expecting that at all. And it's related to range-based for loops. If you are maybe following up the discussions from the committee, you might already know where I'm getting to that, but if not, let's follow along. So in this scenario, what we have is basically just a function that returns by value a vector, and we just want to iterate over that vector, printing out the values, and we will iterate that in some different ways. The first way is just creating an object that will be that vector that we are going to iterate, and iterate over that, and great, 1, 2, 3, as we expected, nothing new here. Another option is that we can directly create or directly call the get values, which will return that object. And again, we can iterate over that, and we will see the result that we were expecting. Another possibility or another scenario is that now we are going to encapsulate that vector. We are going to declare that inside of an object values, and we have a function get that allows to return a constant reference to that object. So again, we can create the object, and by calling get, iterate over that and see the result that we have or that we want. We can instantiate the object and directly access that object, and again, get 1, 2, 3, as we would expect when we are iterating to that. And we could, for example, instantiate the object and call function get, which would expect, of course, to print 1, 2, 3, but then it doesn't. Then it's undefined behavior. And to understand why this is happening here, we can make use of CPP Insights, which is a great tool for you to better understand close to what the compiler is seeing from your code. And in the case of a range-based for loop, what it does is something like that. It's a little bit of slideware just to make things easier here, But basically, it creates a range based on what you have passed on your range-based for. It creates some iterators, and then it uses like the raw loops that we know and love, maybe, to iterate over that and do whatever we want. So in the scenario where we are creating an object and accessing directly the member, the vector here, then we have the lifetime extension kicking in. So although we are creating an object, a temporary object, we are accessing the member directly. So this all works fine. The iterators, they are completely valid, and we get the result that we want. Now, if we take a look at how it would happen if we were to construct an object and call get, which I'm just putting here just to remind everyone, it just returns a constant reference to the vector that lives inside the object, then we don't have the lifetime extension. So whenever we try to use that range, whenever we try to access that, that's a dangling pointer. So dangling reference. So that's what causes the undefined behavior in this case. So luck for us, this got fixed in C++ 23. And the fix is basically another rule that will specify that the temporary objects that are constructed in range-based for loops, they should live as long as the loop executes. I'm just simplifying that a little bit. And with all of that together, I can now share with you what was the problem and what was my flaw, the flaw of my reasoning when I was hitting this issue. So I'll just allow you to take a look quickly here. So what was I thinking when I saw this code? Of course, it's a very simplified version of the code. The code itself that I was working on was for sure a lot more complex than that. But here's what I was thinking. So I do have a temporary object foo. This temporary object is created, and from that I call getBar, which creates another temporary object. So although I have created foo, because I'm only interested in bar, then the lock that existed on foo, then the foo object itself would be already released. And then when I get to do something which also uses the same mutex that I had on foo, then it would be all fine. But as we saw today, that is not the case. Because, again, the temporary objects, they are destroyed as the last step of when evaluating the foo expression. So when I got this example, what was really happening is that foo here was holding the mutex that I needed for do something, so nothing was really happening. So I did have a kind of a deadlock, and it was really painful to get to understand this, but at the same time, when I finally did, and I finally understood that I wasn't understanding the full picture of object lifetime, then it was pretty much easy to fix, and then the code works fine now. So, sorry. So, what we have talked here, we talk about object lifetime. We talked briefly about the rules for starting, what are the rules for the lifetime of an object to start, to finish it. We talk about dangling references. I don't think it was really news to anyone, but I do wish you all the best dealing with your dangling references. We talk about lifetime extensions, but mostly we talk about the lifetime of temporaries and what are the common pitfalls that you might fall when you are dealing with temporary objects. With that, thank you a lot, and I'll be taking questions.
Hi, thank you for the talk. Could you go a little bit more into detail about what is considered a scope in terms of the initializer list of a constructor?
You mean so the question was regarding the last example, or not the last example, but one of the last, sorry everyone, it's a whole bunch of slides. But are you talking about this initializer list exception? I didn't fully understood.
I mean, when you're constructing an object, you have a member initializer list, and then after the initializer list, you have like another block, which is like after the constructor. So how do they interact? Are they two completely separate scopes?
I didn't really fully understand this question, sorry, but we can talk later about that, if that's okay.
Okay, slide number 183.
182?
183, yeah. Yeah, here. So, could you please repeat again why on line? What's the problem on line 15?
On line 15? So the problem on line 15 here is that we are creating a temporary object, foo4, and we are accessing, we are calling a function that returns a constant reference. For the rules of lifetime extension, calling a function that returns something does not qualify as something that motivates or justifies the lifetime extension. So the compiler doesn't really, no, I'm not saying correct, but the language doesn't really allow this to be the reason for lifetime extension. So basically, you are just, it would be the same as creating an object, accessing or getting this reference, and then delete that object, and then using the reference.
Okay, so that's the main difference between line 13 and 15.
Line 30?
13 and 15. That's the main difference.
Yes. It's the direct access of a member, then it's lifetime extension, and just indirectly through functions accessing that.
Okay. Also, like you've clearly explained that when we take a reference to a temporary, then it extends the lifetime of it. Is there any advantage of doing it though? Like it's generally not like common thing to do. I mean, at least in my understanding. So is there any advantage of doing that in terms of performance?
You mean, if I understood your question, is there any benefit of doing lifetime extension?
For a temporary, in the sense like,
the temporary.
Even if we don't do that, even if we directly catch it into a variable, you spoke about return value optimization, so there is no copy done in general. So my understanding is that there is no performance gain or like any advantage of doing it, but is there any advantage doing this way? No.
To be honest, I don't know that.
Okay.
I mean, I can try to reason, but I don't think it would be like a valid answer for that.
Okay. Sorry for holding up the line. One last question. So in the, I think it's around slide 49. We don't need to go there, but like when we throw an exception, the constructor doesn't get called. So I know that, but I just wanted to know like what really happens under the hood. So when we are actually inside the constructor, is the storage already allocated for that object or not? So if it is already allocated, how does it internally know? By it, maybe I'm referencing to compiler. I'm not very sure about that. So how does it really know that we should not call destructor for it if the storage was already allocated? That's my last question.
Yeah, so I'm not really, I don't usually really go that deep. So my understanding is that in this case, the allocation, the location for the object itself, it happens, the location, and you could, for example, have on the constructor allocation of arrays or anything like that. This would happen, but the object will not. I mean, those are two different things, you know. But what I know for sure is that the compiler will not kind of try to see what you have done and try to roll back. No, the compiler will just stop at that moment and just return the execution to the cache or whatever, and that storage will be allocated.
Thank you for your presentation. If you can go to slide 181, please.
181?
I guess, or the slide before, just before, not the lines maybe. Before. Yes, more, I guess. I'm not yes, exactly. So here, if we see line 10, I guess we would have a dangling reference, no? If the get bar returning a ref, shouldn't we have a dangling reference when we execute at runtime?
You mean the reference from the... let me take my...
Because here the...
So you mean the reference
Yes.
that I'm taking here as a
Yes.
parameter?
Yeah.
If the question is it has something to do with...
No, we will have an undefined behavior because we will have a dangling reference here because the get bar, I suppose it returns a reference to the bar, and you're passing it, and the foo is now out-destructed, and you will have a dangling reference.
But in this case, bar is not destructed. So...
It's not, because isn't it the member of foo?
No, but I mean, foo is created,
Okay.
and it's created in the mirror of this evaluation,
Okay.
as well as bar is created during that. So my understanding is that it will not be undefined behavior because bar would still be alive until the end. But I would probably test that as well. It might be the case really that because we are creating, but I don't think so.
Okay. Thank you.
Hi, and thanks for the talk. I had two questions, really. First, concerning the lifetime of static objects. Plenty of objects that manage dynamically allocated memory. And let's say we have a static instance of this object, which invokes the destructor of that static object, which calls delete. Common examples are a lot of STL containers, strings. Is this in some sort of like aspect UB, or guaranteed to not be UB by the standard?
Yeah, I believe that it should not be UB. Yeah, I'm not 100% sure though. I believe we will need to try and take a look at that. So I really focus towards automatic, mostly towards automatic variables here and objects. So I might be missing something related to static. So I'm sorry, I don't know this answer.
Sure. And my next question was, when we have the lifetime extension, when we do return by value, does that invoke copy, or does that transfer the ownership of that object completely over to the caller?
So it doesn't involve any copy.
Sure.
So when we have lifetime extension, and maybe I can find an example here. Yeah, this one. So what we have really is the object being created. Mm-hmm. So the full object being created, as well as we have a reference being created. And then we have some sort of linkage between those that the reference will not really trigger or call any kind of copy constructor. We just have the object being there and just referring, the reference referring to that object.
Okay, so in this instance, the destructor will not get called.
The destructor will be called because the object in here, it's a temporary object that was constructed. But the main thing about reference lifetime extension is when the destructor is called. So if you were to have just a simple object being called and constructed, when the scope ends, the object will be destroyed.
Right, as in like the destructor will be called exactly once at the end of its proper lifetime.
And
Sure.
this will be the same for the lifetime extension, but the lifetime of that temporary object that was created will be destroyed when the lifetime of the reference finishes.
Sure. Excellent. Thank you.
Hey, thanks a bunch for the talk. It was really fun. So if you could talk just for a second about lifetime extension for const L value references versus non-const L value references. I was under the impression that extension only happens for const L value references. But when you showed the standard, it seemed like it just said references.
Yes.
So I'm not sure if I just wasn't reading it correctly or what's going on.
So
there.
as you can see here from the message that we get on the scenario where we don't have, because we need the reference to be const, then it mentions that a non-const L value reference. So when I was reviewing everything, I have the same impression, but my feeling, which I don't really, I'm not certain about that, but I have strong feelings that somewhere in the standard it will be a rule that specifies that, and maybe it was somewhere that I might have just quickly went through that. So thank you, everyone.